ever wondered how a massive factory can churn out thousands of perfect items an hour? Or how a city's water supply just works flawlessly 24/7? Well, behind all of that automation, there's a mastermind. They're called controls engineers, and they are the unseen architects of our modern world. Today, we're going to pull back the curtain and see what they really do. Okay, so becoming a controls engineer, it starts in the classroom with some pretty heavy theory. But what happens when all that academic knowledge hits the noisy, messy, high-stakes reality of the factory floor? Let's dive into that gap. You know, this is the million-dollar question. It's something aspiring engineers ask all the time. You spend years in school wrestling with incredibly dense math and theory, but you almost never get a clear picture of what the day-to-day job is actually like. So, let's break it down. And this right here says it all. In university, you're buried in these super abstract concepts, like Nyquist plots, right? These complex graphs that tell you if a system is going to be stable or just spiral out of control. But then you get into the real world, you're way more likely to be programming a PLC, that's a tough-as-nails industrial computer, or, getting a frantic call at 2 a.m. because a machine that costs the company thousands of dollars a minute is down. It's a huge shift from theoretical math to hands-on, high-pressure problem solving. And that really is the core of the job, solving big, industrial-sized problems. A controls engineer isn't just sitting behind a desk designing things. No way. They are world-class troubleshooters who diagnose, fix, and optimize complex systems when the pressure is really on. So try to picture this. You're an engineer. Let's call you Samir. You walk into a chemical plant control room, and it is absolute chaos. The system is screaming out over 10,000 alarms per day. That's more than one every 10 seconds. The operators are so overwhelmed, they've basically started ignoring the whole system. I mean, where do you even start with a mess like that? This is where the real engineering kicks in. Samir didn't panic. He just systematically dug into the data. He analyzed all those alarm reports, hunting down the noisiest parts of the system. He found dozens of control loops that were totally out of whack and pinpointed actual hardware problems with some control valves. So then he reconfigured the software and worked with the mechanics to get the physical gear fixed. It's this perfect mix of digital detective work and real-world teamwork. And the result of all that work? A staggering 99% drop in all those useless alarms. Just think about that for a second. He took a system that was a screaming, dangerous liability and turned it back into a useful, reliable tool. He made the whole plant safer and more efficient, all in one go. That just shows you the incredible impact one good controls engineer can have. And this mission isn't just happening in chemical plants. Oh no. You've got engineers like Gail Dwyer over at Corning figuring out how to get giant industrial robots to handle the very glass that's on your phone. And then you have engineers at places like the Cherokee Metropolitan District making sure the incredibly complex systems that deliver clean water to thousands of homes are running perfectly. The field is just massive. So, what do these engineers actually use to work all this magic? Well, their toolkit is this fascinating blend of super sophisticated software and some seriously rugged hardware. Let's take a look inside the bag. First up, we've got the PLC. This is the absolute workhorse of manufacturing. Think of it as a super durable, specialized computer that's built to do one thing really, really well: high-speed, repetitive tasks. It's the brain that tells a bottling machine exactly when to fill, when to cap, and when to send the bottle down the line, thousands and thousands of times a day without ever missing a beat. And then you've got its bigger cousin, the DCS, or Distributed Control System. This is the big picture brain. So while a PLC might run a single machine, a DCS is like the mission control for an entire plant. We're talking about massive operations like a power station or an oil refinery, where thousands of variables like temperature, flow, and pressure all have to be kept in perfect balance 24/7. This chart really breaks it down nicely. PLCs are your go-to for fast, individual tasks. They're programmed with something called ladder logic, which is pretty straightforward to pick up. A DCS, on the other hand, is built for huge, plant-wide processes where reliability is everything. The programming is more complex, and yeah, the upfront cost is way higher. The bottom line is, you gotta pick the right tool for the scale of the problem you're trying to solve. But hey, it's not all digital. Controls engineers are hands-on and they need physical tools. I love this quote from a user on Reddit. It just perfectly captures that professional pride they take in their craft. I mean, these folks often work in pretty tough environments, so having reliable tools isn't a luxury. It's an absolute necessity. So what's in the bag? Well, first, you've got the command center. The laptop, loaded with specialized software and a mess of network cables and adapters. For diagnostics, a high-end process meter is your best friend for troubleshooting tricky electrical signals. Then you've got your core hand tools. We're talking precision screwdrivers, pliers, cutters from brands you can trust. And of course, you never go anywhere without your safety gear. All right, so maybe you're intrigued. You're thinking, this sounds pretty cool. What does it actually take to become a controls engineer? Let's look at the career path. It's a combination of formal education and a whole lot of deep, hands-on experience. Let's just follow the journey of Gail Dyer. For her, the spark was ignited at a tech camp back in high school. That led her to a mechanical engineering degree. But, and this is so important, she also landed 2 internships to get that real-world experience. After working for a few years, she leveled up her expertise with a master's degree, and that led her straight to the senior role she has today. Her story is a perfect roadmap. It shows that early exposure and practical experience are every bit as important as the degree itself. And when you actually look at job postings, you see what companies are really looking for. Yeah, a strong foundation in math is a given, but look at the rest of this list. They want hands-on PLC programming skills, CAD software proficiency, the ability to read complex electrical and piping diagrams, and, most importantly, killer troubleshooting skills across electrical, mechanical, and hydraulic systems. They don't just want someone who can think, they want someone who can do. So where is all of this heading? Well, the role of the controls engineer is always changing, always evolving. They're more than just a programmer, more than just a hardware expert. They are this unique hybrid, a crucial bridge between the digital world of code and the physical world of machines. If you could map out the DNA of a great controls engineer, these are the traits you would find. They are master problem solvers who absolutely thrive under pressure. They are practical, hands-on people who are not afraid to get their hands dirty to figure something out. They have to be experts in multiple fields, speaking the languages of electrical, mechanical, and software engineering all at once. And because technology is always moving forward, they have to be lifelong learners, just to keep. And that brings us to one last big thought. As automation and AI get smarter and smarter, and our systems become more self-sufficient, the role of the human engineer is definitely going to change. So will they become the grand conductors, orchestrating these incredibly complex symphonies of machines? Or will they become more like the ghost in the machine, that essential but totally invisible expert who keeps the whole show running? It's something to think about.